definition of the power. The power is the time rate of doing a work, or the power is the work done in unit time. Then the power is the derivative of the work with respect to the time t. And we know that the work equals F multiply S. Then the power equals the derivative of F dot S with respect to the time t. We have studied before that if the force is a constant value, then the derivative of F ds with respect to t equals F ds dt. What is the derivative of S with respect to t? The derivative of the displacement with respect to time is the velocity. Then we can write the rule of the power as the power equals the force F multiply the velocity V. Now, what is the unit of measure of power? The power equals dW dt, or the power equals F multiply V. Then the force in Newton and the velocity in meter per second equals 10 power 7 times centimeter per second. The horse equals 75 kilogram weight times meter per second. The horse equal 75 times 10 to the power 5 gram weight centimeter per second. And the horse equals 735 Newton times meter per second. Newton meter equals 10 power 7 9 centimeter. Then the horse equals 735 times 10. And Newton times meter equal joule. Then the horse equals 735 joule per second, which equals watt. Yep. Then the horse equals 735 watt. We know that kilowatt equal 1000 watt. Then the horse equals 0.735 kilowatt. With an example, a person of mass 50 kilogram ascends the stairs of a tower of height 441 meter in time of magnitude 15 minutes. Calculate the average power in watt unit. The force of the man is its weight. Then F equals mg equals 50 kilogram multiply 9.8 meter per second square. Then the force equals 490 Newton. What is the average velocity of this man? The person's average velocity equals distance over time. Distance 441 meter divided time 15 minutes. 15 times 60. Then we divided meter per second. Then the velocity equals 0.49 meter per second. What is the average power? The average power equals force multiply velocity. Force equals 490 times 0.49, which equals 240.1 watt. Dear students, we have very important note. When the body moves with a uniform velocity, uniform motion, then the power is constant and is equal to the product of the force and the uniform velocity. Example, A car of mass 2 tons moves on a horizontal road with a uniform velocity of magnitude 108 km per hour against resistance equivalent to 150 kilogram weight per each ton of the mass. Calculate the power of its engine in horse. The car of mass 2 ton moves with uniform velocity. When a body moves with a uniform velocity according to the Newton first law, then F, the engine force, equal the resistance force. Then F equals R equals 150 kilogram weight times 2 the mass of the car. Then the engine force equals 300 kilogram weight. What is the velocity of the car? It's a uniform velocity of magnitude 108 kilometer per hour. 108 times 5 over 18 equals 30 meter per second. Now we have F in kilogram weight and V in meter per second unit. Then the power equals F times V. F equals 300 kilogram weight multiply 30 meter per second. Then the power equals 9,000 kilogram weight times meter per second. But the required the power of its engine in horse. Then we must change the unit from kilogram weight times meter per second to horse. Then the power equals 900 divided 75 equals 120 horse, which is the power of a car of mass 2 tons moves on a horizontal road with uniform velocity of magnitude 108 kilometer per hour against a resistance equivalent to 150 kilogram weight per each ton of the mass of the car. Dear students, we have another important note. When the body moves with its maximum velocity, then the power is a maximum power, and this is called the maximum power of the engine. Now, let's have an example on this note. A car of mass 9 tons ascends a slope inclined at an angle of sine 1 over 125 to the horizontal with maximum velocity of magnitude 45 kilometer per hour against resistance equivalent to 200 kilogram weight per each ton of the mass. Calculate the power of its engine in horse unit. Now we have a car of mass 9 tons ascends a slope inclined to the horizontal at an angle of sine 1 over 125. The motion is upwards the plane. Now, what is the forces act on the body or on the car in this case? The first force, the engine force F, in the direction of the motion, and we have two forces in the opposite direction of motion. The first one is the component mg sine theta, and the other force is the resistance, which is R in the opposite direction of uniform motion. Now the motion is upwards the plane, and the equation of motion is F equals R plus mg sine theta according to Newton's first law, because the body or the car moves with maximum velocity. Maximum velocity means the motion is uniform motion, and in this case the acceleration of motion equals 0. Then the force or the engine force F equals R plus mg sine theta. Then F equals 200 kilogram times 9, 200 kilogram per each ton, times 9 the number of tons, the mass of the car, times 9.8, then R in this case in Newton unit, plus mg sine theta. M equals 9 ton, multiply 1000 or 10 power 3, multiply 9.8, multiply 1 over 125. Then the force equals 2520 kilogram weight. Now, what about the maximum velocity of the car? The maximum velocity equals 45 multiply 5 over 18 equals 25 over 2 meter per second. Then the maximum power of the car equals F times V equals 2520 times 25 over 2 over 75 equals 420 horse. Then the maximum power of the engine of the car equals 420 horse. Another important note: if the rate of doing work is uniform or constant, then the power equals work over time or equals force times distance over time. Let's have an example on this note. Example: a worker whose job is to load boxes each of mass 30 kilogram on a track if the height of the track equals 0.9 meter. Calculate the number of boxes which the worker can load in time of magnitude 1 minute if his average power is equal to 0.6 horse. We know that the power equals total work over time. Then the power equals number of boxes times work needed to load a one box over time. Then number of boxes needed to load in a 1 minute equals power times time over the work to one box. Power equals 0.6 horse multiply 735 divided 30 times 9.8 times 0.9 in a minute. In a minute equals 0.6 times 735 times 60 over 30 times 9.8 times 0.9. Then we can use the calculator to find the number of boxes needed to be loaded in 1 minute, which equals 100 boxes. Another example: a train of mass 200 tons ascends a slope whose inclination to the horizontal is an angle of sine 1 over 200 with a uniform velocity of magnitude 27 km per hour against resistance to the motion parallel to the direction of the line of the greatest slope of the plane at a rate of 18 kilogram weight per each ton of the mass. What is the power of the engine in horse? And if the train descends on the same plane with the same velocity, what is the power of the engine in this case, supposing the resistance are constant in both cases? Now, the first case, a train of mass 200 ton ascends a slope whose inclination angle to the horizontal sine 1 over 200. What is the force act in the body? In this case, the engine force, the component of the weight mg sine theta, and the resistance of the road. Now we can write the equation of motion. When the train ascends the slope, the motion multiply 18 equal 3,600 kilogram weight, because we have a resistance 18 kilogram weight per each ton of the mass, and the train mass equals to 100 ton, then the resistance, the total resistance equal 3,600 kilogram weight. What is the component weight of the train in the direction of the line of the greatest slope downwards? mg sine theta. M equals to 100 ton, multiply 1,000, then the mass now in kilogram, multiply 1 over 200 sine theta, then the component equals 1,000 kilogram weight. And we have resistance R equals 3,600. Then the train ascends with a uniform velocity, and the force of the engine equaled resistance plus the component of the weight. Resistance equal 3,600 kilogram weight plus the component of the train weight equals 1,000. Then the force of the engine equals 4,600 kilogram weight. Now, what about the power of the engine of the train? The power equals F multiply V. F1, where F1 is the force of the engine and V is the velocity when the train ascend the inclined plane. Now, the power equals the magnitude of the force, which equals 4,600 kilogram weight, multiplies the velocity, which equals 27 kilometer per hour. 27 kilometer per hour times 5 over 18, then the velocity in this case in meter per second. Then the power equals 4,600 times 27 times 5 over 18 times 1 over 75. Then the power equal 460 horse. The second case, when the train descends the slope. When the train descends the slope. The second case, when the train descends the slope. In this case, what is the forces act on the body? We have mg sine theta, the component of the weight of the train in the direction of motion downward, and the engine force F in the direction of its motion. And we have the resistance in the opposite direction of the motion of the train, because the resistance parallel to the plane of motion and in the opposite direction of the motion. Now, the train descends with a uniform velocity, then the force of the engine plus the component of the weight resistance equals the resistance. The force of the engine plus 1,000 equals 1,000 is the component of the weight, equal the resistance, which equals 3,600. Then the force of the engine equal 3,600 minus 1,000 equals 2,600 kilogram weight. Now, what about the power? The power equals F2 times V, where F2 is the force of the engine, V is the velocity. Now, the train descends downwards, then the power equals 2,600 multiply the same velocity 27 kilometer per hour times 5 over 18 times 1 over 75. The engine power equals 260 horse. Another example. A particle of mass 1 kilogram moves under the action of a force vector F equals 3I plus 4J such that its displacement vector S is given as a function of time by the relation vector S equals 3t power 2 I plus 6tj, where vector I and vector j are two perpendicular unit vectors. Find the work done by the force, then find the power when t equals 2 seconds. If F measured in Newton, S in meter, and time t in second. Now we have a force, constant force, and variable displacement or variable velocity. Then we must use the derivative of the work with respect to time to find the power of the engine. Then we have studied before that the work W equals vector F dot vector S. Vector F 3 and 4 dot vector S 3t power 2 and 6t. Then the work equals 9t power 2 plus 24t. We know that the power equals the rate of change of work with respect to time or the derivative of the work with respect to time. Now, what is the derivative of the work? 18t plus 24. 18t, the derivative of 9t power 2, 24, the derivative of 24t. What is the power when t equals 2 seconds? When t equals 2 seconds, then the power equals 18 times 2 plus 24. 18 times 2 equals 36 plus 24, then the power equals 60 joule per second. Now, dear students, we have a very important note. What is the relation between the work and the power if the power is variable? The work equals definite integral of the power with respect to time from t1 to t2. Let's have an example on this note. Example: if the power of an engine at any time measured in second is equal to 9t power 2 plus 4t, find the work done by the engine during the first 3 minutes, then find the work done during the 4th second. We know that the power is the rate of change of the work with respect to time. The power equals dw dt, then the work W equals definite integral of the power from t1 to t2 with respect to the time t. Then the work done during the first 3 seconds equals integration, definite integral of 9t power 2 plus 4t from 0 to 3. Integration of 9t power 2 equals 3t power 3 plus 2t power 2 from 0 to 3. Then the work equals 3 multiplied 3 power 3 plus 2 multiplied 3 power 2 between two bracket minus 3 times 0 power 3 plus 2 times 0 power 2. Then the work equals 99 work unit. What about the work done during the 4th second? The 4th second from time 3 to time 4. Then the work equals 3t power 3 plus 2t power 2 from 3 to 4. And we can substitute in this relation. Then the work equals 3 multiply 4 to the power 3 plus 2 multiply 4 to the power 2 minus 3 to the power 3 plus 2 to the power 2, which equals 125 work unit. The time taken by a car of mass 1,200 kilogram to reach the velocity 126 kilometer per hour from rest. If the power of the engine is constant and equal to 125 horse. We know that the work W equals definite integral of the power with respect to time t from t1 to t2. We have the power equals 125 horse. Then the work W equals integration 125 times 735 dt with respect to t from 0 to t. Then the work equals 125 multiply 735 t. We know that the work equal the change in kinetic energy. Then half m multiply between two bracket v square minus v naught squared equals 125 times 735 times t. The velocity of the car equals 126 kilometer per hour. Then half multiply the mass of the car, which equal 1,200 kilogram, multiply its velocity 126 times 5 over 18 meter per second squared to the power 2 minus the initial velocity 0 because the car started its motion from rest equals 125 times 735 t. The left hand side equals 735 times 1000 equals the right hand side 125 times 735 t. Then the time t equals 8 seconds. And by this example we come to the end of our program today. Until we meet again, it's goodbye.